Welcome to the Peacademia course on the basics of semiconductors. This is the second part of the MOSFET lecture. Let's start. By the time you finish this lesson, you will learn N-channel and P-channel MOSFETs, enhancement and depletion mode MOSFETs, MOSFET structure, MOSFET I-V diagram, and the ohmic and saturation regions. In the previous lecture, I discussed the MOS diode or capacitor. It is a time to introduce the MOSFET. As you remember, a way to categorize MOSFETs is to name them P-channel and N-channel. On the left, you can see the structure of an N-channel MOSFET, and on the right, that of the P-channel MOSFET. As we progress through this lecture, you'll see the logic behind this naming. In almost 95% of power electronics applications, N-channel MOSFETs are used. Therefore, I discussed the fundamental of MOSFETs through working with the N-channel MOSFET. What I will discuss is also applicable to the P-channel MOSFET in a symmetrical manner. In an N-channel MOSFET, the substrate is a P-type semiconductor. On the surface of the substrate, there are two highly doped N-type semiconductors connected to ohmic contacts. One of them is called source and the other drain. The MOSFET structure is symmetrical, and you may think that there is no difference between the drain and source. In one sense, it is true, but the subtle difference is that to not allow the substrate to become float, it is normally connected internally to the source. Later, you'll see why the source is called source and the drain is called the drain. On the top surface of the MOSFET, in the area between the drain and source, there is an oxide layer. This layer is electrically isolated. On top of this layer, there is an ohmic contact, which is called the gate. If you disregard the two N+ regions and only focus on this area, what you can see is a MOS capacitor. This is why the MOS capacitor discussion is relevant to MOSFETs. As you can see, the two N+ semiconductors are doped in a P substrate. Therefore, we have two PN junctions. As we already know, whenever there is a PN junction, there is a depletion region too. Note that the MOSFET is not yet biased. From the source contact to drain contact, if we look carefully, we can see two back-to-back diodes installed in series. So applying a voltage with whatever polarity does not cause any conductivity if the substrate is not connected to the source. But since we normally connect the substrate to the source, one of the diodes is short circuit, and therefore this MOSFET can be modeled with only a diode when unbiased. So if I apply a positive voltage between drain and source, no current conductivity is observed. However, the other way, the MOSFET conducts. Note that this is the case when we are talking about the enhancement mode MOSFET. I'll explain what does the enhancement mode means later in this lecture. What I want to do now is applying a voltage source which is positive terminal connected to the gate and negative terminal to the source. Note that the source is connected to the substrate. Now, I want you to focus on this area before I increase VG. This highlighted area shows that we have a MOS capacitor. I discussed the details of the MOS capacitor in the previous lecture. So by assuming that you watched that lecture and you understood the contents, I skipped the details of the MOS capacitor operation hereafter. All right, let's increase VG. By doing so, we get to a point that near the surface of the substrate under the gate, a depletion region forms. If I continue increasing the gate voltage, a thin inversion layer is created under the gate. This inversion layer is N-type and connects the two N+ semiconductors to each other. In fact, a channel is created connecting the drain to source. This is why we call this MOSFET N-channel. If the channel under the gate was of P-type, we would have called the MOSFET a P-channel MOSFET. Now that the channel is created, we need to investigate what happens if a positive voltage is applied between the drain and source. Once this voltage is applied, an electric field is generated directed from the drain to source. This electric field near the drain contact is strong and is zero in strength at the source contact. As a result, the electrons in the inversion channel closer to the drain contact are more accelerated and the channel near the drain gets shallower. If I keep increasing the drain to source voltage, we get to a point where the channel at the drain edge gets closed. After this point, the MOSFET is in the saturation region. Before that, the MOSFET was in the linear region. Talking about the MOSFET being in the saturation or linear region might be a bit foggy at this time, but it gets crystal clear when I show you the I-V diagram of this device. Since the source region is supplying electrons in this process, the MOSFET pin is called the source. And since the drain region is where the electrons leave the device, this pin of the MOSFET is called the drain. Let's continue increasing the drain to source voltage. By doing so, the width of the channel gets smaller and smaller. Although you may observe that the channel is not connected to the drain anymore, there is still a flow of electron currents from the source to the drain. How is it possible? It is possible due to the electric field directed from the drain to source. Once an electron in the channel gets close to the edge of the channel and depletion region, the electron is seized by the field and pushed toward the drain. So this was a brief description of what is happening in a MOSFET. To get a better insight into the electrical properties of this MOSFET, let's take a closer look at the I-V diagram. The x-axis is the drain to source voltage, the y-axis is the drain current. If VG is 0, there is no depletion region and therefore no channel under the gate. Under these conditions, as long as VDS is smaller than the breakdown voltage, no current will flow from the drain to source. By giving the N-channel MOSFET a positive gate voltage, you can observe that the MOSFET conducts. The higher the gate voltage, the stronger the channel, and therefore a larger current can flow through the device. This region is called the linear region. In this region, the MOSFET shows ohmic behavior. In other words, it is a resistor whose resistance is controlled by the gate voltage. In power electronics, we need to engage MOSFETs in this region. This region is called saturation. We call this region saturation because in this region, ID is almost independent from VDS, and it primarily depends on the gate to source voltage. In case you want to use a MOSFET as an amplifier, you need to engage the MOSFET in the saturation region. In the saturation region, ID is calculated using this equation. All this said, how do we know a MOSFET is in the linear region or saturation? How can we examine it? The condition of having an N-channel MOSFET in the off state is that the gate to source voltage is smaller than the threshold voltage. If the gate to source voltage is larger than the threshold voltage, and the difference between the drain to source voltage and the gate to source voltage is smaller than the threshold voltage, the N-channel MOSFET is in the linear region. And if the gate to source voltage is larger than the threshold voltage, and the difference between the drain to source and gate to source voltages is larger than the threshold voltage, the N-channel MOSFET is in the saturation region. In the linear region, the drain current can be calculated using this equation. In the saturation region, this equation gives us the drain current. In these two equations, mu is the mobility of free electrons, C oxide is the capacitance of the MOS capacitor existing in the area between the drain and source, W is the width of the channel, and L is the length of the channel. I want to spend some time to talk about the enhancement mode and depletion mode MOSFETs. In terms of the structure, they are kind of the same. The main difference between enhancement and depletion mode MOSFETs is that in enhancement mode MOSFETs, the channel is not formed when unbiased. However, in depletion mode MOSFETs, the channel is already formed when unbiased. So in power electronics, since we use normally MOSFETs as switches, it is a must to know that enhancement mode MOSFETs are normally off switches and the depletion mode MOSFETs are normally on switches. To turn off a depletion mode MOSFET, you need a negative voltage on the gate. So far, you may have ended up to this question that how come that in the depletion mode MOSFETs there is a channel even when it is not biased. The trick here lies in the trapped charges in the gate oxide layer. During the manufacturing, the manufacturer can control the trapped charges in the gate oxide layer. If there are enough trapped charges, the channel can be created. To disappear this channel, you need to apply a negative voltage to the gate to confront the electric field caused by the trapped charges. In circuit schematics, we use these symbols to represent enhancement mode MOSFETs. This one for the N channel and the other one for the P channel. These symbols are used for the depletion mode MOSFETs for N channel and P channel. In this lecture, I discussed the N channel and P channel MOSFETs, enhancement and depletion mode MOSFETs, MOSFET structure, MOSFET I-V diagram, and the ohmic and saturation regions. In the next lecture, I will cover IGBTs. Thanks for joining this lecture of Peacademia.